of geosciences. Does this work? Can you hear me?
Yes, very clear.
My topic today is modeling of a retrofitting methodology to revive abandoned oil reservoirs. My co-authors are Kewen Li and Yun Han. With the development of oil reservoirs, massive oil wells have been and will be abandoned due to low oil production. According to the report by Reuters in 2020, there are more than 29 million abandoned oil wells in the world, but we cannot leave them alone as potential greenhouse gas or even toxic fluid would escape, which does great harm to the environment and people's health. Much cost would be spent on abandoning oil wells, especially for those offshore. It will be an interesting option if the well can be retrofitted for other uses. This picture illustrated most of the geothermal resources such as shallow geothermal, hydrothermal, and hot dry rock. What we concentrate is the oil reservoirs, where massive oil wells will be abandoned. When the temperature is heated up, the mobility of the oil is enhanced. We used the in situ combustion method to enhance oil recovery, at the same time make an artificial geothermal reservoir. In situ combustion is a known technology, so it's possible to use this kind of method. But the CO2 will bring to the surface with the oil when applying traditional in situ combustion, which we want to avoid. As you can see, we designed the in situ combustion on the anticline, where the injection well is higher than the production well. The CO2 would live in the ground as a result of the gravity separation when the depth difference between injection and production well is great enough, and we have already achieved this concept by numerical simulation. We can use the designed in situ combustion method to enhance oil recovery and create artificial geothermal reservoir. But how can we effectively extract heat? We conducted in situ combustion using CMG star simulator and want to investigate whether it can enhance oil recovery and reservoir temperature. A homogeneous reservoir is established. As can be seen from the chart, the oil recovery can be as high as 70% after 10 years of air injection. Due to the gravitational diffraction effect, the residue oil in the upper reservoir is roughly swept, and a huge amount of oil could be extracted when applying in situ combustion. Besides, a huge amount of heat generated when applying in situ combustion. When the combustion front approaches to heat exchanger, the temperature is about 400 degrees centigrade. With the continuous injection of air, the temperature will decrease and has a long decline stage. This is helpful for extracting heat for a very long time. A huge amount of heat generated when applying in situ combustion. Temperature will affect the mobility of oil. It will be easier to flow when the reservoir is heated. We also modeled the temperature effect on oil, gas, water relative permeability. The oil recovery simulated with the temperature-dependent curves is higher than that with the temperature-independent curves, and the increment is decreasing with the increasing in initial oil saturation, and the relative permeability curves have a great effect on the simulated oil recovery. Besides, we also infect the effect of oil reservoir thickness, initial oil saturation and injection volume on oil recovery and temperature. The oil thickness and injection shows little effect on the final recovery, but it contributes to a higher oil recovery rate. And the oil recovery rate and final oil recovery both increase with the initial oil saturation, but with a decreasing increment. We also investigated the effect of these parameters on reservoir temperature. The reservoir temperature can reach the peak temperature in a shorter time with smaller oil thickness, but with a low peak temperature. The initial oil saturation shows little effect on the peak temperature, but higher oil saturation has a lower temperature decreasing rate. And the reservoir temperature can reach the peak temperature in a shorter time and higher temperature with a higher injection volume. Based on the above findings, it's possible to create an artificial geothermal reservoir, but the CO2 will bring to the surface with the oil. We investigate different patterns to prevent the CO2 emission. First, we investigated the geological structure. The daily CO2 production rate in the anticline reservoir is significantly lower than that in the flat reservoir. The gravitational differentiation effect is more significant, which delays CO2 breakthrough time. Also, we investigate the CO2 breakthrough time is postponed with the increase in well spacing, and an apparent increase in the well spacing helps to leave the CO2 in the ground. And for the depth difference, the CO2 would be retained in the ground for at least 50 years when the depth difference is great enough. And if CO2 accumulates at the bottom, CO2 breakthrough will easily occur at the bottom of the production well. We have achieved the goal of enhancing the oil recovery without CO2 production, but how can we effectively extract the heat? There are primarily two systems to extract heat: closed-loop system and open-loop system. Although the coaxial borehole exchanger has a low construction cost, but it also demonstrated a low thermal power. While for the doublet and the production reinjection system, it will take a lot of construction area and much cost. We proposed an enhanced reservoir system, which is composed of two or more sets of parallel fractures. The cold water is injected to the formation, exchanging heat with the surrounding rocks. In situ combustion is applied by injecting air into reservoir and oxidizing the oil to heat up the reservoir. The ERS becomes a heat exchanger, which is similar to boiler of thermal power plant. It should be noted that geothermal energy does not affect oil production. Based on the energy conservation law, we established our modeling flow. First, we set initial conditions and inputs to conduct in situ combustion simulation. Then, the reservoir temperature after in situ combustion predicted by CMG star were set as the input parameter for the coupled system, and the heat exchange between the wellbore and reservoir model were coupled using finite element method by console. Then we got the outlet temperature and the thermal power. Our coupled ERS model is under balanced exploitation condition. We set the basic parameter and boundary conditions of the coupled ERS model. The wellbore is 2,000 meters long, and the temperature gradient is 35 degrees centigrade per kilometer. The initial reservoir temperature is 90 degrees centigrade. After the mesh-dependent analysis and related simulation, we can see the animation of the coupled ERS modeled by console and CMG with time. Daily CO2 production rate in the anticline reservoir is significantly lower than that in the flat reservoir, as shown in the blue line. No CO2 emission would be achieved when the depth difference is great enough. The reservoir temperature gradually increases with time. The water enters into the ERS and produced from the bottom hole. The wellbore or water temperature gradually increases with time as the temperature is heated up by in-situ combustion. Finally, we compared our ERS with doubled and coaxial bottom hole exchanger. From the results, we can see that ERS shows a significant increase in both the outlet temperature and the thermal power. According to the current research, we draw the following conclusions. The aim of co-production of oil heat electricity with scarce CO2 production from abandoned oil wells has been investigated and realized using numerical simulation, and time-dependent relative permeability curves should be applied for a rational simulation result. Under specific conditions, both oil recovery and reservoir temperature could be enhanced with no CO2 emission. The thermal power of the enhanced reservoir system could increase by 3.12 times and 61% after 30 years compared with coaxial and doublet bottom hole exchangers, respectively. And one single abandoned oil well could become a geothermal well, either for direct use or power generation, with economic yield but little retrofitting investment. That's all. Thank you.
Okay, thank you for your presentation. And now the floor is open for the Q&A. Any questions from the audience? If you have questions, please unmute and yeah. Yeah, I suppose Juliana may have some question. Also, the work on the geothermal development. Yeah. Okay, maybe I have a question. Yeah. So it's also about the well selection for criteria for the which wells are proper for geothermal recovery, geothermal development, and then which one are not good candidate for geothermal development.
Okay, thanks for your questions. First, we just set up a conceptual model, and what we concentrate is that the temperature gradient is high, and also the permeability of the reservoir is high. This is I think the most important part for creating abandoned oil reservoirs, because it's really we need to associate with the water and these two, water flow rate and the outlet temperature. So So we must concentrate on, I think the two parameters are the most important. Yeah.
Okay. Do you have any comments on, maybe where the technology?
I'm sorry, I cannot hear you. I'm sorry, I cannot hear anything. I'm sorry.
Sorry, I
cannot.
lost
Okay.
the internet. Just coming again. So the idea, the EIS is a very attractive idea. I mean, the EIS you propose. Do you have any comments on where the idea is good for use in China? For example, maybe Shengli or Daqing or Xinjiang, maybe.
Yeah. I got the idea from the traditional enhanced geothermal system. It is like a method to enhance the permeability, which is really important for the geothermal production. So I think for the abandoned oil wells, there may be some fractures. They have done some hydraulic fracturing, and these fractures can be used for when the oil wells are abandoned. So this is where I comes from, the idea of using these fractures, which is really
very attractive. Yeah, and also can take advantages of the very likely existing structures for geothermal recovery. Yeah, so that's great.
I just add a little bit more comments for your questions. Okay.
Okay, go ahead.
Yeah. So regarding where we can use this technology, you mentioned a lot of oil fields in China. Actually, most of the oil fields could be applied. I mean, this technology could be applied to those oil fields. For example, Rimon oil field, which is a very old oil field, and actually a lot of oil wells have been abandoned. So basically, regarding your first question, for example, how to choose the candidates. So basically, the main parameters we consider is, Jalen said, so this is the initial oil saturation or the residual oil saturation left behind, or when the oil wells have been abandoned. So basically, the higher the residual, the remaining oil saturation, the better for the application of this technology.
Yeah, so that's right.
Most of the oil fields, because most of the oil wells have been abandoned, have like more than 40% of oil saturation. So
yeah, that's right.
Yeah.
Okay, thank you, Dr. Li.
You're welcome.
Any other questions from the audience? Yeah. Okay.